Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are on lecture 31 today and we are discussing about indentation using an indenter with curved head. Today we will be discussing about the convex head and then we will be discussing about the concave head as well. And this is the list of references, and the last reference in that is the one from which we are discussing this topic. So, in the last lecture we started discussing about this convex indenter. So, this is the frictionless indenter having this convex head, and this has this radius. It is a cylindrical indenter. So, its radius is r, and this is pressing against this elastic half space. This indenter is rigid. So, it deforms this half space, and the deformation is delta at r is equal to 0 here, and the contact radius has a contact circle has a radius of a here. Okay, contact circle has a radius of a here, and Young's modulus of this material is E, and E star is the plane strain Young's modulus, and we have derived this expression for the pressure over here and in the last lecture. So, in terms of delta and h and a, so the h is the height to which this indenter comes in contact with this elastic half space, and the total pressure that is applied is given by this equation 2 E star into a into delta minus 2 h by 3. So, here we have discussed. So, now the question is that we had derived a similar expression using the Hertz mechanics. So, can we get back that Hertz result from this one? So, for that we need to consider that in Hertz, when he derived this equation, he made certain assumptions, and the one assumption is that this capital R, it is actually much larger than A. Okay. So, as a result he came out with this idea that here a delta will be given as a square by r. So, that kind of derivation that he made, and those things we have discussed in earlier. So, what we will like to do is we will substitute this delta as is equal to a square by r in these expressions, these equations, and here h can also be approximated, because in the Hertz mechanics r is capital R is much greater than a. So, we can write it here as r minus r into 1 minus a square by r square square root. So, this can be written as r minus r into 1 minus half of a square by r square, and so this will be equal to a square by 2 r, a square by 2 r. So, h can be written as a square by 2 r. So, we can substitute these expressions. So, delta is equal to a square by r and h is equal to a square by 2 r. So, if we do that, then here we can write this E star into is equal to pi into square root of a square minus r square, and delta is equal to a square by r. So, this is a square by r plus 2 into h is a square by 2 r. So, let us use that. H is a square by 2 capital R into a square here into a square minus 2 r square. That is what we can write. So, here this a square and a square gets cancelled, 2 gets cancelled. So, what I have is E star into pi into square root of a square minus r square, and here I got a 2 a square over r, it is 2 a square by r, and minus we get 2 into r square by r. So, we get here E star into 2 by pi into r, and this is a square by r square, a square minus r square, and it is square root of a square minus r square. So, I get here a square minus r square. So, see the pressure distribution, okay, for indenter, rigid indenter, spherical indenter, okay, this was what was derived. So, this was derived as P0 into square root of a square minus r square. So, if you remember in the Hertz theory, this is what we had derived, and we get back this relation over here. So, what it means is that the expressions that we derived here, that actually we do not need to make this assumption. Okay. So, this expression that we have here is more general form, and Hertz case Hertz theory or Hertz contact mechanics is a smaller set of that, it is that way. And here for example, the same way the total pressure can also be obtained. So, for example, here it is 2 E star into A and delta is A square by R. So, A square by capital R minus 2 by 3 into H is A square by 2 R. So, this is equal to this 2 gets cancelled. So, it is 2 A square by R. So, 2 A square by R is 4 S, 4 it is E star and A square is A cube by R, right. So, that is what we get here. So, it is Newton per meter square meter cube. So, it is Newton, that is fine. So, you see in the Hertz contact mechanics also we got this P total, the total load that is applied in this particular form. So, that is what it is. So, in essence what we have done is that we have presented here is a more general case in which this indenter does not have something like this, that R is much greater than A, that does not have to be there, yet the problem is kind of sorted out. So, now from Hertz mechanics we did it. So, again here it H is equal to A square by 2 R we got, and then P is equal to this. So, finally, capital P is equal to this is what we had gotten from Hertz mechanics. So, P 0 is equal to, it was 3 P by 2 pi A square, and therefore, I can substitute it into this. So, I will get here instead of P 0 I will get here 3 total P by 2 pi and A square is A cube here and square root of A square minus R square. So, that is all it get, this P 0 sorry P as a function of R, and it is R. So, here also if I see here this let us say here E star over R. So, E star over R, E star over R. So, that will be equal to this is 3 into P into R by 4 A cube. So, if I substitute over here, so I will get here 2 by pi into E star over R. So, it will be 3 P R 4 A cube square root of A square minus R square. It will be 3 by 2 into A cube over here, and this is P and square root of A square minus R square. So, 3 P pi also is there. So, pi. So, 3 P by 2 pi A cube. So, basically you see this equation and this equation they match. So, in essence that is what the point that I am trying to make, that in the Hertz contact mechanics this particular approximation that was made, and if that is made, that R is much larger than A, then this approximation is also made, and that makes these relations, the relation that we derived in this formalism, that converges. So, which is good. Now, let us say that we consider the case in which there is adhesion between the punch and this in elastic half space. So, in essence what we are doing is we are trying to pull this, where the punch is being pulled off, that is what it is happening. So, the crack propagating from the edge of the contact area. We want to estimate the critical pull off load. So, that is what we can do here. So, here this is the equation, in presence of adhesion let us punch is being pulled off. So, basically here therefore, it will be E star, we can write here is pi and square root of it is A minus R into A plus R, and over here it is delta plus 2H by A square into A square minus 2 R square. So, in essence we want to find out that if this is the case, then what kind of energy, kind of pull of force that will be required to separate it. So, that is what we will like to figure out, or we will also like to figure out the work of adhesion that we have derived earlier, something like that. So, here at R tends to A, so that means towards the edge, what is the stress. So, that is what we will like to find out. So, P R tends to A. So, this is will be equal to, this is E star and this is pi, it is 2 A into A minus R, and here it is delta plus this is 2 H, it is A square, and this is A square minus 2 R square, right. So, it is a square minus 2 a square. So, it is comes out to be E star into pi into square root of 2 a into a minus r, okay, into this is minus a square goes. So, it is delta minus 2 h. So, this is the pressure. So, it is minus of sigma, or letter here I have written in terms of z the same thing actually I have told you in the earlier, that z is equal to 0. Okay. This is the normal stress. So, normal stress is negative of the pressure, and that is how we can find out. So, this z at z equal to 0. So, that will be equal to minus of this quantity. So, this quantity I will write it as k I by square root of actually square root of 2 pi a minus r, 2 pi a minus r, that is the way I will write it. So, I will have an expression for the stress intensity factor. So, stress intensity factor here. So, we do all that, and the same way we just wrote. So, it will stress intensity factor, no. So, that will come out to be minus of, this is 1 by square root of pi into a, and here it is E star, okay, into delta minus 2 h by, yeah, no, delta, we have done it already. So, it is like this. So, let me just check once. So, yeah, delta minus 2 h, that is there, and it is 1 by square root of pi a, it is a minus sign here, that is there, yes, minus sign also I have it here, delta minus, yeah. So, k I will have a minus sign there, that is okay. So, therefore, the work of adhesion, it is equal to the strain energy release rate, that is equal to k I square by 2 into E star. So, this will give rise to square root of, so it is 1 by pi into a, it is E star whole square delta minus 2 h whole square, okay, by 2 into E star. So, E star will get cancelled here. So, it will be E star, not cancel, E star will be divided by pi 2 pi a into delta minus 2 h square. So, the expressions for this work of adhesion, so that will be here, it will be something like this. This is the work of adhesion expression. Okay. So, we have done that. So, now in here we will like to write it in terms of the load that needs to be applied, the pool of load that needs to be applied. So, here what we will do is instead of delta, okay, we will replace delta here. So, it is P by 2 E star into A. So, that will be equal to delta minus 2 h by 3. So, what it means is delta is equal to P by 2 E square into A plus 2 h by 3. So, what it means is delta minus 2 h. So, delta minus, or rather 2 h minus delta, I should have done that anyway, 2 h minus delta. So, that will be 2 h minus P by 2 E star into A minus 2 h over 3. So, it will be 6 minus 2 4 h. So, it is 4 h by 3 minus P by 2 E star into A, good, like that. So, here therefore, so let me substitute it. So, it will be work of adhesion. So, that will be E star by 2 pi a into 2 h minus delta whole square. So, that is actually 4 h by 3 minus P by 2 E star by a whole square. So, this is what it will come out to be. So, I think we can write it in a different form also. So, here now let us say that if we want to compare it with the JKR contact mechanics, right, JKR equation, then we can substitute this approximation that we do for considering that elastic half space. So, it is h is a square by 2 r. So, let us substitute that over here. So, if we do that, it will be E star by 2 pi into a into minus P by 2 E star into a plus this is 4 h by 3. So, 4 by 3. So, remember that in JKR mechanics JKR equation we have got not h, but we have everything in terms of a, that is the contact radius, and the capital R, that is the diameter or radius of the indenter, that in that manner. So, therefore, we need to do this exercise. So, h will be replaced by a square by 2 r and this is whole square. So, what we get here is E star by 2 pi a and this is minus, this is p by 2 E star into a plus. So, this is 2 by 3 a square by r, a square by r whole square. Okay. So, if we can recover, that is the idea, that is what we are trying to do. So, here this is what I get. Now, this is W8 work of adhesion. So, let us say that what was the form in JKR. So, so here yeah, that is what we did. So, so E star has to be replaced by 4 by 3. So, I will do that and finally, we will come out with this idea, right. So, E star will be replaced by 4 E star by 3. So, K, capital K is equal to 4 E star over 3. So, this is the way I write. So, from here E star is goes as 3 capital K by 4. So, here we will write here E star 3 capital K. So, 3 capital K by 8 pi into A and minus this is P and E star is 3 K by 4. So, it is 2 into this is 3 K by into 4 into A here plus this is 2 by 3 into A square by R whole square. So, this 2 and this 2 gets cancelled. So, it is 2 by 3 K, this is 3 K, this is cross here. Okay. So, this is 2 by 3. So, you take out 2 by 3 outside is 4 by 9. So, 4 by 9 is 3 by 8 into K into pi into A and this is let us say 4 by 9 here. This is minus and this is P by capital K into A plus this is A square by R whole square. So, this is 4, it gets 2 and this is 3, this is 3. So, I have 1 upon K by 6 pi A. So, it is K by 6 pi into A into minus P by K into A plus A square by R whole square, like that. We are gradually converging to whatever JKR. So, basically we have now this expression that is WA work of adhesion is equal to this and this one. If we can rearrange that, so the K we take it outside. So, we will get here, rearranging means K we take it outside, we get this and we can further rearrange it. Let me do it, further rearrange. So, let us say this will be W A into 6 pi A K, it is square root of 2. So, that will be equal to minus of P by A plus K A square by R, plus K A square by R and let us divide by square root, so K square by R. So, divide by A here square root. So, it will be W A by 6 pi K to the power square root and minus this is P. So, it will be A to the power square root, I am dividing it. So, it is A to the power 3 by 2 and plus this is K by R and this 2 minus. So, it is also 3 by 2, it is not 3 by 2, it should be 1 by square root by 1 by 2 here. So, if I do it here, so it is also 3 by 2, right. So, A to the power 3 by 2 here and finally, A to the power 3 by 2 by R. So, we get here arrange it, finally arrange it, we get this and this is what we have from the JKR mechanics, that is also the lecture 22-24. So, we can recover that equation by doing this exercise. So, from this analysis, from this this particular problem in which we do not make this JKR or this Hertz this assumptions, we can get back the relations for the JKR, that is the bottom line here. So, that is what we do. So, good. Now, we will like to see convex head. Yeah. So, basically this is the summary of this. So, this part that I did. Now, let us say that we will consider a punch having concave surface having the radius of cylinder, okay, A. Okay. So, it is A should be here. So, we have a different type of punch. So, it is let us say concave surface over here, right. So, the question is that what happens the pressure distribution when this concave surface is first pressed against this indenter. So, remember that this is the indenter and you press against it. So, what happens is something like this. This let us say that concave surface has got this is the surface over here. So, it goes something like this. So, this is the elastic half space and this height is actually h, this height is h, this diameter radius is a here, okay. And now the question is that now after bringing in contact and then there is adhesion between this elastic half space and this indenter, right. And now let us say I pull it off. So, as I pull it off, how much amount of load that will be required, okay, for a given work of adhesion between the two surfaces, that is the question. So, for that what you need to do is first find out the pressure distribution, okay, at the contact area, and then we apply this fracture mechanics approach or by this JKR kind of approach, this is the energy minimization approach, and find out this pull off load. So, I will show you how to do that. So, in a sense what we have is this initially this indenter is subjected to compression loading on the elastic half space. So, it goes inside, okay, it presses inside. So, h is the height here and there is an intimate contact between the punch and the surface of the elastic half space, although this is a frictionless contact, remember this is a frictionless contact, okay. So, we are staying and now if we pull it off, what will be the pull off load that is required, that is what you want to know. So, when you pull it off, it will pull off something like this. So, question is that with respect to a flat surface, is there any enhancement in the pull off load because of this particular geometry? And then the next question appears is that now we consider a spherical geometry, but what is a more optimized geometry at which this enhancement, if at all it is there, that will be maximum. So, is there any enhancement or an advantage by keeping an indenter or in this particular form, this curved concave shape, okay, while pulling it off while in this kind of adhesion adhesive design or adhesion measurement. So, indeed there is, that is what I will like to show you. So, here first thing is that we need to find out what will be the pressure distribution at the area contact area areas. So, we will get into that, and so before that we have to find out that when this indenter is pressed against. So, what is this vertical displacement or vertical deformation V, okay. So, at within this contact radius, that is r less than a. So, V at z is equal to 0 is of this particular form. It varies with r is this parabolic form, but if of course it is spherical. So, this equation will take care of that. So, at r is equal to 0, r is equal to 0. So, here r is equal to a, V 0 is delta j, see this is the delta here, r is equal to a, and r is equal to 0 here, okay, this is delta minus h, this distance, right, that is the way it is. So, let us say we substitute here. So, this is r is equal to 0 here. So, it is delta minus h is equal to a and r is equal to a here, and here it is let us say delta is equal to a plus b into a square. So, this is equal to delta minus h plus b a square. So, delta delta gets cancelled. So, b comes out to be what, h by a square. So, therefore, this we can write this v at z is equal to 0 equal to a is delta minus h plus this is h by a square into r square, that is all we can write. So, we can therefore remember that we have to find out that derivative, not derivative, I do not think derivative, we have to now see how we do that. So, we have to find out this. So, we have to find out this particular expression g1 s or g1 as a function of t or s, okay, using this equation. So, that we have to do, right. So, we will do that now. So, Here we have to follow these equations, this procedures that we have discussed in the last lecture. So, here first we have to determine this G1s using this equation, and then we have to use whatever G1 we estimate, and we have to substitute here to get this pressure distribution PR as a function of R, and then from there we get the total load, etc. So, we will take up this analysis in the next lecture. Thank you.